Hello students, welcome to the continuing series of videos on differential equations, and now we'll take a look at an example where we do some verification and we solve for a specific case of a solution to a differential equation. So it says verify that the general solution is correct and use the initial condition to find a particular solution. So this is basically saying that this equation is a solution, or the claim, right? The claim is that this solution here, this equation, is a solution to this equation. Okay. So that y equals c e to the negative 2x is a solution to this particular equation. And then we'll work on the initial conditions in a little bit. So let's just verify and check the claim, okay, or to check the claim. Okay. And this is just intended for you to get some practice in seeing how differential equations work. So first, we have to find y prime, and y prime is negative 2c e to the negative 2x. And if we apply it to this particular equation, y prime plus 2y is equal to negative 2c e to the negative 2x plus 2y, so that's 2 times c e to the negative 2x. That does in fact equal 0. So done, claim has been verified. In the next part, we're asked that the initial condition is that y is equal to 3 when x is equal to 0, and we want to find a specific solution. In other words, for the initial condition, we want to find a specific value of c. So the claim is that every solution, every equation that looks like this with some constant in front of it is a solution to this equation, and we want to find a specific value of c such that y equals 3 whenever x equals 0. So doing this isn't too difficult either. So we start with this equation, y equals c e to the negative 2x, when y is equal to 3, so we make the substitution. Then x is equal to 0, and that means that e to the 0th is just 1, so that's just that. So that means c is equal to 3. So the specific solution is y is equal to 3 e to the negative 2x. Okay. So that's the solution, the specific solution for the given initial conditions. We're going to move on and take a look at a case where we're expected to actually solve the equations. So far, all we've been doing is given a problem and a potential solution, see if it works. Now we're going to actually solve something without having it given to us first. So here we want to find a function y such that this expression here is true. Okay, and we're going to do this by separating variables. So essentially putting all the variables that use y together and all the variables that use x together. Okay, and it's a little bit easier to think about this problem using Leibniz notation. So dy dx is equal to 2x over y. And then we can separate these variables, multiply both sides by y, and multiply both sides by dx. Okay. So now you have y dy is equal to 2x dx. Then we can integrate, okay, and then look at the results of this problem. Okay. So there you have it. I've integrated it, and I got that this is equal to 1/2 y squared plus some constant, and over here it's x squared plus some other constant. and we can do some simplification here. So we can say that y squared is 1/2 y squared is equal to x squared plus c2 minus c1. But this here is also a constant on its own. So then we can just think of this as 1/2 y squared equals x squared plus some constant. Right? We don't need to have two constants. We can just combine them together, make it a little bit simpler. And then some textbooks or some questions will expect you to write it without any fractional coefficient. So we can look at it this way. I'm going to move everything to the left. So I'm going to say 1/2 y squared minus x squared equals c. And then I'm going to multiply everything by 2. So that's going to give me y squared minus 2x squared equals 2c. But again, this is still a constant. Okay. So then anytime I have a complex constant, I'm just going to combine it and make it into a simpler version. So my final answer will be y squared minus 2x squared equals big C, or some constant. Okay. So now you have it. This is a general solution. So this is basically saying if I have an equation like this, when I take its derivative and I apply it in this form, then this differential equation will in fact be true. Okay. Now we need to move on and solve for this specific condition when x is equal to 0, y is equal to 3. Okay. So I'll write it here. So we're going to solve the specific case of this solution. In other words, find c. And it says here that when y is equal to 3, x is equal to 0. So this basically means that 9 is equal to c. So our specific solution is y squared minus 2x squared equals 9. Okay. So what we've done here essentially is given some sort of relation between the function y and its derivative, we can somehow figure out the specific function that satisfies this condition. And so far this has been very abstract, so let me give you a very practical problem here. Okay. The population of a species is initially 288 and has a growth rate that depends on its population given in the table below. Find a function that models its population with respect to time t. So this is one column here is the population of the species. On the other side is its growth rate at that point. So you can see here that when the population is about 347, this is how fast it's growing. When it's about just a little bit under 10,000, this is how fast it's growing. So in other words, like all biological populations, the more that you have of the species, the faster that it's going to grow. Okay? And the question that makes this challenging is, how do we find a function that models this right here? Usually we're given t and the population. Now we're just given the population and the growth rate. Okay? And I'm going to leave you to solve this problem on your own. This is actually the difficult quote-unquote problem. But I will leave you with a bit of a hint. I would say to all of you, start by making this graph. Okay. So start by graphing the population on the horizontal axis and the growth rate on the vertical axis, and see if you can find some pattern from that, and then go from there. Thank you for watching. Make sure you work on this problem earnestly. Have a wonderful day.